Okay. Zoom that in a little bit. All right, like I said, we're our introduction to proof. And it starts out okay with algebraic proofs. When we get to the geometry proofs in another chapter, that's where it gets a little more challenging. But it starts out okay. So what is a proof? A proof is an argument that uses logic, definitions, properties, and previously proven statements. Previously proven statements to show a conclusion. And like I said, we're moving into algebraic proofs, and I think you'll do really well with these. This whole first table here is all of the properties of equality that you've been using since you started solving equations. So the first one is called the addition property of equality. And in symbols, this is what it says. If you have a balanced equation, A equals B, then it's perfectly legal in algebra. If you add something to the left to keep it balanced, you add the same amount to the right. So that would look like, say, A plus C would equal B plus C. So all I've done is add C to the left and add C to the right. So an example of where you might actually use the addition property of equality, say you had the equation x minus 4 equals 6. So we have a balanced equation. This x minus 4 would represent our A information. The 6 would represent the B. If you were going to solve this, what would you do to both sides of this equation? And if you add 4 to the left, you add 4 to the right. That's an example of using the addition property of equality. So we'll move on to the subtraction property of equality. Starts out the same way. If you have this balanced equation, left side equaling right side, A equals B, then the subtraction property of equality says it's perfectly legal to subtract the same amount to both sides and it'll still stay a balanced equation. So that would look like A subtract C would equal B subtract C. Still balanced. Yep.
I'm a mess.
You're a mess.
I'll get over it.
Okay. So say you had the equation x plus 5 equals 2. So there's our balanced equation. If you were going to solve, what would you do to both sides? Subtract 5. That's an example of the subtraction property of equality when you subtract the same amount from both sides. You know, I don't care what the final answer is here. I'm just looking at the property we're using. You've got your multiplication property of equality. And these all start out the same on the first 4. If A is equal to B, actually the first, 4, then again, it's perfectly legal to multiply both sides by the same amount. So that would mean A times C would equal B times C. So again, an example, say you had the equation x over 3 equals 5. And you were going to solve this for x. What would you do to this left-hand side of the equation? You would multiply by 3 to get that to cancel out. So we're going to multiply both sides by 3. That would be an example of using the multiplication property of equality. And then the last one that's going to be very easy to pick up on, the division property of equality. If A equals B, then perfectly legal to divide both sides by the same amount. So A divided by C would equal B divided by C. So here, if we had 4x equals 24, what could you do to both sides to solve? You're going to divide by 4 on both sides. That's the division property of equality. Okay, very easy because of what you're actually doing to both sides. This next little chunk of 3 might not be as familiar to you. The reflexive property, when you see reflexive, think of reflection. When you look in a mirror, what do you see? Yourself. The reflexive property of equality just says a number is equal to itself. No kidding. So reflexive, think reflection. It might help you to remember that one. All right, now symmetric property of equality. If A is equal to B, then the symmetric property says it's okay to switch sides of the equal sign. Then B should equal A. An example there, if I said 2 was equal to X, you would be legal to say that X equals 2 by symmetric property. Okay, transitive property. Very much like that law of syllogism that we just had, where it was kind of linked together. The transitive property says if A is equal to B, and we know that B is equal to C, then the transitive property lets us say that 2 other things are equal. Do you know what those 2, Reese?
A and C.
A would equal C. Because they're both equal to B, they would have to be equal to each other. That's transitive property. So if we said if Y is equal to, let's go 3 squared, and we know that 3 squared is equal to 9, by transitive property, what would we be able to say? Y equals 9. Okay, distributive property, you're familiar with this one. Distributive property says if you have A times the quantity B plus C, then by distributive property, we would be, what does distributive property say? You should know this one. What do we do?
A times B.
Plus B times C would be another way to say that. I'm just going to do the one part of it. So then distributive property lets you multiply the A into both of them and drop parentheses. So then you would get A times B plus A times C. That's distributive property. So if we had 3x plus 4, we would be able to use distributive property and expand that to 3x plus 12. And for some reason, I copied distributive twice. But the substitution one's a little bit long, so we're going to use both boxes to write the definition for substitution. And this is pretty basic too. So substitution says if A is equal to B, then B can be substituted for A in any expression. So when would we use this? So if x was equal to 5, and I asked you to find the value of 3x plus 6, you could use substitution to do that. So all substitution does is wherever I see an x, I'm allowed to put in a 5 because they're equal. So this would give me 3 times 5 plus 6, which would give us a 21. That's substitution. Okay, our last three properties are for congruence. Remember, congruence is for shapes. So that top big table, those are the properties of equality. That was for numbers. Numbers, because we don't add shapes, we don't multiply shapes. We have congruence for shapes, and there's only three properties here. We have matching, reflexive, symmetric, transitive. Reflexive, symmetric, transitive. Here, I said think of reflexive as a reflection. A number is equal to itself. Here, a figure is going to be congruent to itself. So reflexive, figure A is congruent to itself. Examples of things we might be writing down the road. Angle B is congruent to itself. Segment DE is congruent to itself. Or two examples. So shapes aren't equal, they are congruent. So we have the reflexive property of, oh, I forgot to put the symbol here, congruence. I put a little congruence right there. Okay, symmetric property is where we switch sides of the equal sign up here. We're going to switch sides of the congruent sign here. So if figure A is congruent to figure B, then we can switch. Figure B is congruent to figure A. So an example of something we might be writing later on, if angle A happens to be congruent to angle B, then we can say angle B is congruent to angle A. Again, all kind of common sense stuff here. And then our last property is that transitive property where we kind of chain link things. So if figure A is congruent to figure B, and figure B is congruent to figure C, then if you logically link them together, which two are congruent? A to C. So an example, if segment AB is congruent to segment CD, and segment CD is congruent to segment EF, Then take a look. AB is congruent to CD. CD is congruent to EF. Which two? AB to EF would be congruent by transitive property. Okay, that's all I wanted to get done was get this obnoxious table out of the way. Tomorrow we'll be using those properties in our algebraic proofs. Good times to come tomorrow. Oh, we are done for the day, so you two online can check out. We still got, what, a few minutes left?